Good late morning, everyone. All right, so there's a question on the screen. Feel free to get started with it. In terms of announcements, nothing that I haven't said a few times already. Test number 5, the last one, gets going tomorrow or Wednesday, Monday, depending on when your tutorial is. It covers up to and including section 1.8. And that's all I really have to say. Oh, it's not actually sharing? That's weird. Oh, it's good now? All right. Beautiful. Yeah. No. 1.8. Up to and including 1.8. All right, if anyone has any other questions, feel free to fire them off. Is the determinant the same as the cross product since both deals with areas? They're not the same thing. They're related to each other, but they're not the same. We can use the determinant to help us find the cross product, but we use the determinant for many things that don't involve the cross product. So they're certainly not the same thing. They're obviously related to each other, but they're not the same. If anyone has any other questions, feel free to fire them off. If not, there's now a question on your screen. So I'll give you another minute or two to get started with that one. Yeah. So I guess, maybe I should be more clear because I was blurring the lines a little bit between 1.8 and 4.9 upon further reflection. So basically, in terms of the difference between the two, 4.9 is when we started listing off the specific types of transformations. Like 1.8 is when we were doing transformations and operators in general and their properties and all that kind of stuff. The difference with 4.9 is, so for example, we wouldn't ask you, do the rotation operator, do the reflection operator, do the dilation operator, that kind of stuff. That's 4.9. All the stuff that we were doing transformations and finding standard matrices, that's 1.8. And so that is fair game. What isn't fair game for test 5 is like us actually saying do a reflection or do a rotation, those specific types. That's what wouldn't be included because it's in 4.9. Or, oh, well, I didn't even notice that was a private question. I shouldn't have answered that as punishment for private questions. Great question. Anyone got an answer for that? What's the difference between rotating counterclockwise and rotating clockwise? So one is going this direction, one is going this direction. So what would the difference be? And I drew something and I didn't actually put it. Yeah, so counterclockwise is this first one. And this one is clockwise because it goes around like a clock goes around. doesn't necessarily. I mean, the quadrant is more related to what the angle is to give you the quadrant, not the direction and how you get there. Do you talk about column spaces in linear algebra 2? Yes, you talk about column spaces in linear algebra 2, which is a special case of something called a vector space, which, as you can probably guess from the word, has a lot of the same properties that vectors have. True, the order in which it hits the quadrant would depend upon whether you're going clockwise or counterclockwise, for sure. All right, so we have this right here. We want to find our standard matrix. So T is a linear operator on R2, starting by going clockwise by a certain angle, dilating by a factor of 3, reflecting it about the y-axis. So the key question here is rotating clockwise. We know rotations is our more complicated one. The other two are much more straightforward. The clockwise is the more complicated one. So when we're doing clockwise by 2 pi over 3, when we're finding the standard matrix, what angle are we using? Not pi by 3. Yeah, we're using negative 2 pi by 3. The fact that we're going clockwise instead of counterclockwise means, as I kind of drew before and then erased it, we're going in this direction. And that's the negative angle direction, which I don't think what I said actually is a word, is a phrase, but the idea is the angle is becoming negative. Now, if you wanted to, so negative 2 pi by 3 would hit us here. If you wanted to, you could think of it as the same thing as going all the way around clockwise. And you could get different angles that give you the same thing. So I'm gonna stick with negative 2 pi by 3 for educational purposes, but for example, 4 pi by 3 would be the same thing. Give you the exact same angle. Technically, adding and subtracting any multiple of 2 pi gives you the exact same thing. All right, so anyway, back to the question. So that's the angle we're talking about for the first of 3 things. So how are we going to find the standard matrix for this linear operator? And I've heard in the tutorials some of the TAs have been showing other things as well. All right, so plugging in theta would be for just the first of 3 parts of it. But kind of how do we do the whole thing overall? There's a couple options. Right, but again, that's for the first part of it. How do we deal with the whole thing overall? That's a piece of the puzzle, not the whole puzzle. Right, so one option, and technically this isn't part of the course, but I've heard that the TAs were talking about this in the tutorials, at least in some of the tutorials, and that's fine, there's nothing wrong with it. But it's technically not part of the course, is that we can actually find the 3 standard matrices and multiply them together. So I'll address that at the end. That wasn't my intention when I gave the question. But it does work, and so I'll address that at the end. So pretending like we know nothing about the fact that these things multiply together, can anyone think of another way that we could have done this other than taking our 3 things and slamming them together? What's our other way of finding a standard matrix if we don't have the coordinates? Really not sure what it means by that. Go in order of what? Yeah, we could apply the standard matrix to our elementary vectors. That's right. So that's what I'm going to do here. I'll relate it back to what some people were saying about multiplying matrices together, and I'll come back to that afterwards. But my intention when I gave the question was that nobody knew that you could multiply them together and that we would just apply it to the standard matrix or standard vector. So we're going to find 1, 0, and we're going to take 1, 0. We're going to perform these three things in order and then see what we get afterwards. And so if we do the rotation, to rotate, I'm going to say rotate by negative 2 pi over 3. What happens to the vector 1, 0 when we rotate it by negative 2 pi over 3? And this is part of what we did on Tuesday. What does the rotation do to 1, 0? And if you're trying to figure that out, I mean, this was the first column in that standard matrix. So what do we get? Either the actual answer or even the intermediate step along the way. And so what we get here, so if you recall back, it was cosine of theta, sine of theta. That's what happened to the vector 1, 0 when we rotated it by theta. In this case, theta is going to be negative 2 pi by 3. So it's cosine of negative 2 pi by 3, sine of negative 2 pi by 3. So cosine of negative 2 pi by 3 is just equal to negative a half. Sine of negative 2 pi by 3 is negative root 3 over 2. So there's our rotation. That's the more complicated one. The other two are much less complicated. Any questions, though, about other than how to find trig values? And feel free to talk to me after class if you're still working on your trig values. But in terms of what we do, any questions about how we manage to get our rotation? I'm not really sure what you mean by that question. Yes, it is. Yeah, I mean, I didn't use that, but you could use the fact that cos of negative 2 pi by 3 is equal to cosine of positive 2 pi by 3. It's equal to negative a half either way. Not really sure what you mean by doing it like that. Okay. Yeah, because that's what happens. Sure, we could. Because that's what we saw last class, is that if we took 1, 0 and we rotated it, cos theta, sine theta is where it ended up. That was part of what we were talking about on Tuesday. I'm not going to claim that's the only way to do it, but it certainly works. All right, so what is a dilation by a factor of 3? What does that do to the vector? Just multiplies it by 3. So that's negative 3 over 2, negative 3 root 3 over 2. And then as for the reflection, what is reflecting about the y-axis due to a vector? We reflect about the y-axis. That's right, the x changes sign. So in this case, it was already negative. So changing the sign becomes positive. And so t of 1, 0 is equal to 3 halves negative 3 root 3 over 2. There we go. And we'll do the exact same thing with 0, 1 to get the second column, and then we'll stick them together in order to find our standard matrix T. Right. So again, because it was 3 steps in terms of doing this, we had to perform the 3 operations. I believe somebody mentioned that making sure we're doing them in order, and that is absolutely vital. Sometimes by coincidence, you can get the same answer if you do them in different orders, but in general, the order is going to affect things. If you do the reflection, then the rotation, you're going to get something different. All right, so any questions about how we found t of 1, 0 before we move to t of 0, 1? All right, so same deal, rotate. So again, if we're rotating 1, 0, again, let's keep it general for just 1 second. In terms of theta, what do we get when we rotate it 0, 1 by a factor or by an angle of theta? And again, if you're looking for the answer to this, it was our second column in our standard matrix for the rotation. Not quite. That was close. Yeah, the sine part would be negative. So negative sine theta. So again, if we're doing it by negative 2 pi over 3, we get y negative. So the reason it was negative for the x was negative was wrapped up in the picture that we saw on Tuesday, where since we're starting at 0, 1, if we started, and again, we did this from the point of view of theta being positive, but the idea would still be similar, that if we rotated it, we're no longer going into quadrant 1, we're starting by going into quadrant 2, which means the x would be negative of what sine theta would give us. It was all wrapped up in terms of what we talked about on Tuesday. So that's where the negative came from. Of course, if the theta is bigger than 90 degrees or going in the opposite direction, then, I mean, the sign itself could be negative, and a negative of a negative is positive, but in terms of the formula, that's where the negative came from. So plugging in negative 2 pi over 3, or 4 pi by 3, or negative 120 degrees, if you're still living in a degree world. Either way, we're going to get, what's that, root 3 over 2 and negative a half. Okay, so again, the rotation's the most complicated part. The other ones are slightly less complicated. So any questions about how we managed to do the rotation? Right, dilation as it was before, multiplies through by 3. Reflection as it did before made the x negative. In this case, it started positive and became negative, so there's our t of 0, 1. And what do we do with this t of 1, 0 and t of 0, 1? What do we do with them in order to make our standard matrix? T of 1, 0 is the first column, 3 halves, negative 3 root 3 over 2, negative 3 root 3 over 2, negative 3 halves. What happens if we have R3? So the way we handle R3, and we talked about this very briefly at the end of class on Tuesday, the way we would handle R3 is we would just rotate along the z-axis. So in the xy plane, nothing changes in R3. So if we're doing a rotation in R3, nothing changes for the x's and y's. We still get cos theta, sine theta. We still get negative sine and cosine. And the z just stays the same because we're only going to be rotating. And I don't know if that's really showing anything. But the idea is we're just rotating it in the xy plane. So the z remains exactly where it was before. Any other questions about how we managed to solve for this? Here with my whatever tablet pen, and I'm just doing this, and you can't actually see it rotate, I don't think, so that was probably completely useless. All right, in terms of an aside, so some people mentioned matrix multiplication. So this is an aside. Technically, it's part of 4.10, so feel free to read it if you just want it for curiosity reasons. Feel free to just read it on your own. But the idea is we can think of t. Now, this is not a transformation thing. This is a function thing. So what we're doing here is we're doing one operation, the reflection or the rotation. Then we do a second one. And then we do a third one. It's not that we don't plug in the z value for R3. It's that it's constant. It stays the same. So when you plug it in, you get the exact same thing coming out when it comes to a rotation in R3. If you're rotating in relation to the xy plane. All right, so anyway, so again, this is an aside. You don't need to know this. It's part of 4.10 in case you're curious, which is part of our book, but it's not part of our course. So the first one can be thought of as you perform one operation, the rotation, then a second one, the dilation, then the third one, reflection. So it's one operation, then we plug that into the second one, then we plug that into a third one. What type of function do you get if you do one operation, then a second, and then a third? What kind of function do we call that? Again, not necessary for you to know, but hopefully you've heard this word before in high school. Where you stick one function into another, it's a composition, that's right. So we can actually think of this as one function inside another function inside a third. Right. So instead of just one transformation, this is really three transformations composed together. So if you're doing this, and again, there's theory behind this that we're not going to talk about here because it's not technically part of the course, is that if you wanted to find the standard matrix, then you can find the individual standard matrices and multiply them together. Now, for any composition, you always work from the inside out. Order of operations, you do the inside bracket first. So you're working from the inside out, and so it kind of looks like it's going from right to left. And that's reflected in the fact that our matrix multiplication would go from the right to the left. In other words, we could have done this using ideas from 4.10, where we would find, first of all, our last transformation, which was the reflection, so -1001. T2 was a dilation by a factor of 3, so 3003, and T1 was the reflection, so we could use, the rotation, so we could use our standard matrix for a rotation. So this is an alternative way. It's nothing I would expect students to know because it is not technically part of the course, but it is something that works. Technically, the book would go over what it means to be a composition, showing compositions are linear to begin with, and then eventually proving that this idea works. And so we could have come up with hopefully the same answer this way as well. -3003. This would be -1/2, -√3/2, √3/2, and -1/2. And then assuming I don't screw anything up, did I not do that? Cosine is the first column, and negative sine cosine is the second column. So if you're writing that as rows, then no, it wouldn't be. What is this? 3/2, -3√3/2, -3√3/2, and -3/2. And if we look, that's exactly what we got above. All right. So again, the secondary way is not something you need to know. If you're curious about it, feel free to, ask me about it a little bit more. But for time reasons, we don't get into compositions of linear transformations. We just hit the basics. All right. Anyway, back to the question, the actual question, using it to find t of 2, -3. So how do we use our standard matrix to find t of 2, -3? So we just take our standard matrix, multiply it by 2, -3. So whether we use it from the first one or the second one, it was the same thing. And so what do we get? 3 plus 9 √3 over 2. And -3 √3 plus 9/2. So that's what would happen if you took 2 -√3, rotated it, dilated it, and reflected it. This is where we'd end up. All right, so any questions about this example or any of this linear transformation or operator type questions before we move on to something slightly different? All right. So, how many marks would that question be? 1, 2, 3, 4, 5, 6, 7 or 8. Probably one for each piece of finding t of 1, 0. Same for 0, 1. Maybe 7, 8, 9, maybe 9. That's what I was talking about. So we wrote out the standard matrix. So that's the one where the z would stay the same and the x's and y's would be exactly the same as a rotation in R2. Miss the final matrix? Oh, sorry, right here. Beautiful. All right, so reviewing some of the main concepts, now we're jumping into chapter 5. So again, I go over this in more detail in the pre-lecture videos, but the idea is we're talking about something called an eigenvalue and eventually something called eigenvectors. So an eigenvalue of a linear operator, we'll talk about why it has to be an operator in just a second, but the eigenvalues of a linear operator are when t of x is equal to this constant, so this is the Greek letter lambda. With the pandemic, we're getting used to some Greek letters. The Greek letter lambda, where t of x is equal to lambda times x. Geometrically speaking, what does it mean for t of x to be equal to lambda times x? So completely geometrically, what does that mean? Right. With the exception of lambda being 0, what we put into the function x from the domain and what comes out of the function, which is a constant times x, are parallel to each other. So geometrically speaking, and we'll see some examples from this point of view, the input is parallel to the output. All right, now because any of these linear transformations can be thought of as matrix multiplication, whether we're using t of x or we're using a times x, really there's no difference between the two. So our focus is going to be at first looking at a times x as matrix multiplication in order to get used to the ideas, but we could do this for transformations as well, just letting a be the matrix for that transformation. All right, so I say A has to be a square matrix. Why does A have to be a square matrix in order for this to make sense? You don't think we have this? Did I not post the slides? Oh, I posted the wrong slides. Oh, that's unfortunate. So you put my linear algebra 2 class where I did this as a review. Boom. All right. Now the correct ones are posted. My apologies. Oh, these slides are 1300. I must have posted my other classes too. But if you wanted to look at those slides and learn about complex vector spaces, you go right ahead. All right. Anyway, even if you didn't have them, I did just post the correct slides. That being said, I'll try and go through these a little bit slower, just because, or at least for today, just because you don't have them ahead of time. All right. Anyway, so this is what an eigenvalue or an eigenvector is. I'm not just reviewing eigenvalues. We're actually going to go through it right from the beginning. All right. So anyway, but of course you all did the pre-lecture videos, so should be something that makes sense. So we're basically trying to solve ax is equal to lambda x. So there should be one obvious solution to a times x equals lambda times x. So one really obvious solution for x. What is that obvious solution? Yeah, the zero vector. Of course, the zero vector is going to be a solution to this. So the real question is not, when do we get solutions? Because we always get solutions no matter what lambda is if we allow x equals 0. Our real question is, what values of lambda, if any, do we get non-zero solutions? All right, so back to my original question, why does a have to be square for any of this to make sense? And it might even be easier to answer this question from the point of view of the linear transformation. All right, well, I'll deal with what I've posted a little bit later. I'll have to figure out what went wrong there, but let's just stick with this. So why does the transformation, why does that standard matrix have to be square? In order for it to be parallel, I mean, something doesn't need to be true because 5 steps later something has to happen. It has to go from Rn to Rn. Why is that? Why can't it go from Rn to Rm? Why does the domain have to equal the codomain? And it has to do with this parallel thing, right? The x and lambda times x, if you take an x and multiply it by lambda, you're not changing the dimension. So lambda times x is the same dimension, is in the same dimension that x would be in. That's why the transformation has to have the same domain and codomain, and hence why the T has to have a square standard matrix. It's just to make sure the dimensions all work out. And I didn't mean it to be that crazy of an example, so never mind. Let's go. So here's an example, and I'm going to write it out because this is that here. So the question is, let's find an eigenvalue for a if a times 1, negative 2, 3 is equal to negative 4, 8, negative 12, and 2 eigenvectors. So give this question a try. sure that I don't have these slides up there now? Might just be something stuck in the cache type issue. Yeah. For those that are still seeing the wrong slides, it might just be that it's in your cache or cache. I don't know how to pronounce that. All right, so the purpose of this example is to get used to, I mean, this is not necessarily a calculation type example. This is just straight up going to be a understanding example. So what would be an eigenvalue for this? If A times this vector is equal to this other vector, what is the eigenvalue? -4. Where are we getting -4 from? Where are we getting -4 from? Factor out the -4, 1, -2, 3. In other words, here's x, here's lambda, here's x, and we get ax is equal to lambda x, which is exactly, and x is not 0, which is exactly what being an eigenvalue is all about. So in other words, lambda is equal to -4. Now, I'm not saying -4 is the only eigenvalue of this matrix. I mean, we need to know more about the matrix to be able to answer that, but we know -4 is a eigenvalue, or an eigenvalue of the matrix. All right, so any questions about why -4 is an eigenvalue? All right, so there should be one obvious eigenvector of A corresponding to this -4. There should be one obvious one. So the question asks for two, so we can talk about a not so obvious one. But what should be one obvious eigenvector in this question? When we're talking about eigenvectors, we're talking about the x. So the longer it takes, the less obvious my obvious one is. But yeah, 1, -2, 3. So the lambda is the constant. The eigenvector is the x, or at least the non-zero x, because, well, that's what eigenvectors are, the non-trivial solutions. All right, so the real key here is what would a second one be? And we'll get to that. But any questions about how we got the eigenvalue and how we got one of the eigenvectors? So it's all about having non-zero solutions to ax equals lambda x. That's what being an eigenvalue and an eigenvector is all about. Non-zero solutions to that specific expression. So the eigenvector is just x, absolutely. So the eigenvalue is the lambda, the eigenvector is the x. All right, so can anyone think of another x? Because the question asked for 2. So where are we getting 2, -4, 6 from? Yeah, so can we just multiply by 2? So I'm going to take this and Just multiply it by 2. So that's the same thing as A of 2 times 1 negative 2, 3. Now we could actually work with this, but we know what A times X is. So how are we supposed to do it if there's a 2 in there? What can we do with that 2? Other side of what? Yeah, and not the other side of the equation, no. Maybe. We might get a different lambda. We'll have to see. Yeah, the other side of A. So 2 times. Like, this is not an equation we're solving. We're not solving an equation here. We're finding out A times this new matrix. So we're not solving an equation. So we're not dividing 2 on both sides. But we can factor it out of the matrix. That's a matrix property. And this is 2 times, what were we given in the question? 4, 8, negative 12. So that's negative 8, 16, negative 24. So we computed A times 2, negative 4, 6. We got negative 8, 16, 24. And it shouldn't be too complicated to see that this was equal to twice what we had originally. So what happens? Can we factor out negative 4 again? Because somebody said 2. There's nothing special about the 2. We'll talk about that in just a second. But can we factor out negative 4 again? Certainly we can. And what do you know? We get, here's x, and here's x again. So in other words, 2, negative 4, 6 is another. Could I have done this with 3 and done 3, negative 6, and 9? And just factored out a 3 instead of factoring out a 2? Or is something super special about the 2? There's nothing special about the 2. In general, if x is an eigenvector, so is any multiple of x, any non-zero multiple of x, because technically 0 is not an eigenvector. All right. So again, what I want you to get out of this example is what is an eigenvector. We'll spend the rest of today and a bunch of time on Tuesday talking about how to find eigenvectors, how to find eigenvalues, all that kind of stuff. That's going to be our focus there. We're going to come up with formulas and all this kind of stuff. But in terms of what an eigenvalue or an eigenvector is, it's solutions to ax equals lambda x. Can the eigenvalue change? So I'm not saying that, for example, here, I'm not saying negative 4 is the only eigenvalue. So, I mean, in our next example, we'll talk about how to find all the eigenvalues. So that's going to be our focus for the rest of class, is how to find these eigenvalues. So we're going to see that usually multiple eigenvalues do work, right? But multiplying by a constant won't change the eigenvalue. It'll just change the eigenvector. Yeah, lambda is the eigenvalue. So the question about eigenspace. So in general, the eigenspace is the set, because I'm tired of saying non-trivial or non-zero, is the set of all eigenvectors plus the zero vector. basically because I want to stop having to say the non-zero solutions. So eigenspace will just lump the zero into that. In other words, it's just all the solutions to ax equals lambda x. So that's what we mean by eigenspace. So in this case here, k times x would be in the eigenspace. Technically, we haven't given a reason why there couldn't be other stuff, but that's all going to be part of the process of what we do going forward. So we'll be able to answer these questions a little bit better once we do some more examples. Speaking of more examples, see if you can find the characteristic polynomial and compute the eigenvalues. Forget about the eigenvectors for just for this one for now, and just compute the eigenvalues of this 2 by 2 matrix A. Are we going to finish 5.1 today? I mean, we'll get through all the main ideas. I might have some more examples for us to go over on Tuesday. But the main idea is the 5.1 we should get through today. All right, so we want to solve ax is equal to lambda x. So this is the main idea. I wouldn't say this is part of the solution here, but these are just the ideas. So we want to solve this equation, or specifically solve for lambda where this has non-zero solutions. So, I mean, we'll combine the x's together, because if you thought about dividing by x, you make me sad. So we'll move everything to one side. We'll factor out the x. And then x isn't 0, so we'll have to do something with the other thing. All right, so well, not everything I wrote here, but the last thing I wrote is really just plain garbage. What's garbage about the last thing that I just wrote? Yeah, what's garbage about it is the fact that one is a number, the other is a matrix, and that makes no sense. How we fix it, as some people mentioned, and we saw this when we did the standard matrix for a dilation in 4.9, where we wanted to think of it not as constant multiples, but matrix multiplication. And the way we did that is we stuck an identity there, because we know that doesn't change anything. And so we end up getting lambda I minus A times x. So again, this is to make sure everything still makes sense. It doesn't change what our answer would be. And we want to know, when does this has non-trivial solutions? So we have a square matrix. It's a confusing looking square matrix, but a square matrix times x is equal to 0, and we want it to have more than just the 0 solution. When does that happen? Right, when the matrix there is not invertible. So this happens if and only if the matrix is not invertible, but invertible is kind of an ugly property to use. So what's an equivalent statement to a matrix not being invertible? What about its determinant? If the determinant is 0. The 0 number or the 0 vector. A determinant being non-zero means it is invertible. We want it to be not invertible. Is there a reason for it? To find eigenvalues. So if eigenvalues are your only endgame, then no, it wouldn't matter which one you brought to which side. That wouldn't matter if eigenvalues was your only endgame, which in this class, it's our only endgame. From a higher level idea, the polynomial we're going to create has uses beyond just finding eigenvalues, so that would make a difference. So for the efforts of consistency, I'm going to stick with lambda I minus a, but if you wanted to find eigenvalues, if you did move it and got a minus lambda I, you would still get the same eigenvalues, even though the polynomial would not be the characteristic polynomial half the time. So in this class, we're going to stick with lambda I minus a. All right, so point being is if we want to find the eigenvalues, really we're just solving this equation. The determinant of lambda I minus a is equal to 0. All right, any questions about those ideas before we just start banging away with determinants and polynomials and solving things? All right, so lambda I minus a. So that's going to be the determinant. So our vertical bars, lambda minus 1. So that was the idea. Now we're actually solving it. Lambda minus 1, negative 2, negative 3, lambda minus negative 4. So that's lambda minus 1 times lambda plus 4. We're subtracting a. So lambda I is lambda 0, 0 lambda minus 1, 2, 3, negative 4. And it's a little 2 by 2 determinant. So that's not particularly exciting. So that's lambda squared plus 3 lambda minus 4 minus 6. So lambda squared plus 3 lambda minus 10. All right, and we just want to solve for lambda where this is equal to 0. And that'll tell us exactly when we get non-zero solutions, and we'll focus on how to find those non-zero solutions, in a little bit. All right, so this thing here would be our characteristic polynomial. When the question asks for the characteristic polynomial, that's what this quadratic, or at least for this example, it's a quadratic, is talking about. So lambda squared plus 3 lambda minus 10. All right, so any questions about how we found it before we actually solve it to get the eigenvalues? Yeah, to get the eigenvalues, you'd solve the quadratic. All right, how do we solve the quadratic? 2 is a solution. There's no guarantee it's the only one. How are we getting these numbers? Random guessing and checking? Where the negative 2 and negative 3 come from? So lambda I minus a. So lambda times I is this minus a, which is 1, 2, 3, negative 4. And just subtract them. Set the polynomial equal to 0 and solve for lambda. Well, let's be a bit more specific. How do we solve for lambda was my question. Some people are saying factoring. That's beautiful. So a little factoring, lambda plus 5, lambda minus 2. In other words, lambda is equal to 2 and negative 5. Again, it's a quadratic, so we could use the quadratic formula. That's always a good tool to have in our toolbox, is the quadratic formula, which also works. This one factors, so yay for us. All right, If you have any questions about this one, feel free to keep firing them off. Otherwise, we can try another one. Just write it out. I don't have to leave the page. So feel free to try the next one. Here's a 3x3. So we'll see how things can change there. So I'll give you a couple minutes to give this second one here a try. Sure. What? I mean, anything about solving quadratics is certainly fair game. What row of zeros? I'm not sure what row of zeros you're talking about. Sorry. Like in terms of row reducing and all that kind of stuff? And that, I think I said in my videos, you should always get a row of zeros. Yeah, that's when we're solving for the eigenvectors. So that won't be part of the eigenvalues. That'll be part of getting the eigenvectors. So we'll see that in an example in about 10 minutes. All right, so this is a 3x3 matrix, which obviously has its own unique set of challenges. But the biggest thing when we're doing this is that it turns into finding a 3x3 determinant. Now we'll have lambdas along the diagonal. So in this case, instead of getting lambda squared for our biggest power, we'll get lambda cubed for our biggest power, which again, even that is already going to start to make it a bit more annoying in terms of solving because there's no nice cubic formula. There is a cubic formula, but it involves so much craziness that you might as well not use it. And so, that being said, in terms of actually finding this characteristic polynomial or setting it equal to 0 to get the characteristic equation, I mean, really it's just, hey, a 3x3 determinant instead of a 2x2. All right, anyway, I made this example harder than I intended to. That being said, this can still technically be solved. So I'm not going to just stop. But I will say not every cubic can be nicely solved or even ugly solved kind of in the way we're doing this. I didn't say that. I'm saying probably nicer than this one. That being said, this is certainly solvable. So any ideas as to how we can solve this? So in terms of some ideas, and for those of you who have taken calculus, you would have seen some of these ideas there. Not that you need calculus to use it, you just would have seen some of the same ideas. How can we solve when a cubic is equal to 0? Yes, exactly. We'll plug in values and hope for the best. That's exactly how we're going to do it. So some people are saying we need to have a factor. We can use synthetic division. All that is great, but they both come from the same thing. We got to find a solution to this first. So it's going to turn into just plugging and chugging and hoping that we can get something. So that's why I say this doesn't always work. But can anyone see a value of lambda that you could plug in and a little guess and check? Which is not the greatest thing to have on a test. But guess and check, we can get lambda equals something as a solution. Yeah, lambda equals -1 is a solution. In other words, this thing is going to factor to give us lambda plus 1 times something else. So, but again, that is a guess and check thing, which is an awful test question if you have to rely on students to hopefully guessing and checking the first thing first. So take that for what it is. But if we had a solution, let's say we had one solution, how can we find this other factor? Yeah, some kind of division. And again, I don't want to focus on that and get into a 10-minute discussion on how to divide polynomials. But if you know what that is, then that can be helpful, yeah. We could end up with lambda squared minus 2 lambda with a little bit of division and get the rest of it. That can be done through some kind of polynomial division. Synthetic division, if you know it, works nicely. Long division works fine as well. The rational root theorem, if you know what that is, can be helpful for finding the first solution, but even that's not a perfect thing. All right. Anyway, so we end up getting this. So let's pretend like it was magical and this showed up. Everyone who got tuned out when I said the words were probably not going to say anything crazy like this on a test. Tune back in. What can we do with the quadratic that's left over? If we can factor it, that's great. Anyone see how that factors? No, neither do I. So certainly doesn't seem like this thing factors. And honestly, if we're wrong and it does factor, we'll still get the same answers if we use the quadratic formula anyway. It just involves a little bit more work. So lambda is equal to -b plus or minus the square root of b squared minus 4 times a, which is 1, times c, which is, -4 over 2 times a. In other words, that's 2 plus or minus the square root of 4 plus 16, which is 20, all over 2. There we go. And so, in this case, we get 3 eigenvalues, 1, and a couple things involving square roots. And yes, that simplifies, but that's not my concern. We could simplify it to 1 plus or minus root 5. That's not my focus, but it definitely can be simplified further. All right, any questions about how we did this or kind of did this? All right, let's go back to something a bit more reasonable. See if you can find, again, the characteristic polynomial, but find the eigenvalues of this 4 by 4. Now we're going to make it even harder. Or maybe not harder. So give this question here a try. If you know the property, it's going to be really easy. If you don't know the property, you're going to in about 2 minutes. So again, in terms of how easy the matrix is, how hard the matrix is, we all start from the same place. 0 is equal to this characteristic polynomial. And we just find lambda I minus a. This is a 4 by 4, so there's 16 entries instead of 9 or 4. Looks worse, but we have a bunch of zeros, so that makes it a little bit nicer. What's the determinant of this matrix going to be? Just the product of the diagonal. Lambda minus 1, lambda minus 5, lambda minus 8 times lambda minus 10. So a much easier determinant to compute, easy determinant, easy-ish looking characteristic polynomial, and it's nice because it's already factored. So what are the eigenvalues? So 1, 5, 8, and 10. So even if you hadn't seen the property before, hopefully from this example we can figure it out. What property can we get from this specific type of example? Again, we can prove it as well, but what is the property that might arise from this? So we're done. I mean, this is the end of the question, by the way. So the eigenvalues are 1, 5, 8, and 10. Upper triangular. So if A is upper triangular, then the eigenvalues are the diagonal entries. That's almost right. Yeah. I mean, it's not wrong. We can just do better. Yeah. We don't actually need it to be upper triangular. Any triangular matrix would work as well. And they both come from the fact that we had the determinant property. That the determinant of a triangular matrix, you just multiply along the diagonal. That's what's making this property true. So it works for lower and upper triangular matrices. So in other words, triangular matrices are really, really nice to find their eigenvalues, which shouldn't be a surprise. Triangular matrices have been nice since chapter 1. All right. What's the characteristic polynomial? It's always the thing that's equal to 0. So this is the characteristic polynomial. All right, so let's go back to our 1, 1, 2, 3 example. I can give you enough to do your tutorial this week. So let's just recall for A equals to 1, 2, 3, negative 4. We got 0 was equal to the determinant of lambda I minus a, which was lambda minus 1, negative 2, negative 3, and 4. Our eigenvalues were 2 and negative 5. So find the eigenvectors. So now we know how to find the eigenvalues. Let's find the eigenvectors. Yeah, lambda plus 4. Thank you. I said eigenspaces, so let's be consistent with my notes. Let's find the eigenspaces. They're almost the same. So the eigenvectors and the eigenspaces. So the eigenspace is the collection of all the eigenvectors, but also including 0, so it's technically including one thing that's not an eigenvector, because I don't want to have to keep writing and I shouldn't just say me, I mean, there's more to it than this. But it's in order to kind of complete the picture. Otherwise, we'd have to keep saying except for the zero vector over and over and over again. And again, if you go beyond this course, the fact that we call it an eigenspace, space in this context has a very specific and useful meaning as well. But for this class's point of view, an eigenspace is just the eigenvector, but including zero, so you don't have to exclude it. And sorry, I usually want to give you a bit more time, but we're running a bit low on time today, and I want to finish this example. So what are we trying to do here? What are we trying to solve? We're trying to find the eigenvectors, aka the eigenspace. What are we trying to solve? We're trying to solve for the x. The idea, we want to solve for x, the vector x, where ax is equal to 2 times x. That's what we're trying to solve for. We found the 2, now we want to find the x. That's the same thing as solving for where 0 is equal to 2x minus ax, which is 2I minus a times x. So we're trying to solve for this particular equation. How can we do that? How can we solve for matrix times x equals 0? How do we solve that? Row operations, exactly. And 2I minus a, well, here's 2I minus a. Well, except we'd have to plug in lambda equals 2. So in other words, we're taking the same matrix that gave us the characteristic polynomial, and now we're plugging 2 into that. In other words, we're getting 1, -2, -3, and lambda plus 4, augmented with 0, 0, and we're solving. And then after we've done this, we'll do the same thing with -5. And so we get row 2 is row 2 plus 3 row 3. There isn't a row 3, so row 1. We get 1, -2, 0, 0, 0, 0. In other words, x2 is equal to t. x1 minus 2x2 is equal to 0, which says x1 is equal to, move to the other side, 2t. And our eigenspace is the set of all vectors. x1 is 2t, x2 is t, and again, t is any real number. Technically, the 0 vector would not be an eigenvector, but for eigenspace, we're including that. We don't have to exclude it. Yeah, that's exactly it. That's exactly it. So we're just taking the same matrix that we had, we're plugging in the eigenvector, and now we're solving for where the x, solving for x that makes it equal to 0, but that's what a system of equations does. So this is just a new system of equations for us to solve. And we could do the same thing, right? So I mentioned in the videos, and someone pointed out to me, why are we always going to get a row of zeros? Be careful here before I go crazy. Why should we always be getting a row of zeros in our coefficient matrix? Because we solved for it in an earlier example. Right. Again, look at our list of equivalent statements. Right. So there's actually two kind of reasons for this. Number one, it's so we get free variables. But we know that's not exactly the same thing. So it actually comes from our list of equivalent statements that says because our coefficient matrix is square, Again, our list of equivalent statements is determinant of A is 0. A is not invertible, and the reduced row echelon form is not equal to the identity. And since the reduced row echelon form is not equal to the identity, we're going to have to get a row of zeros. All right, anyway, plugging in -5, we get a very similar thing. So -6, -3, -3, and if we plugged it into lambda plus 4, we get -1. So all we did here, it's not lambda minus 5, it's lambda equals -5. Where are these coming from? Here. Yeah. So when we found the eigenvalues before. Yeah, so this is the end of lambda equals 2. So now we're doing lambda equals 5. And again, some row operations, and I'm going to blast through the row operations a little quickly. Row 1 is row 1 divided by -6. Sorry, that should be -2. And row 2 is row 2 plus 3 row 1. But everything we're doing here is just solving a system. So finding the eigenvalues or eigenspaces, no, that's just solving a system of equations. So x2 is equal to t, x1 plus a third, x2 is equal to 0. That says x1 is negative a third t. And so our eigenspace is a set of negative a third t, t, where t is a real number. So the new stuff here is really, no, these are two separate eigenspaces. There's an eigenspace for the first eigenvalue. There's a different eigenspace for the second one. If there were 3, there'd be another eigenspace for the third one. There's not, we don't lump them together. Yeah. So the new thing here is the eigenvalues. Finding the eigenvectors is just solving a system of equations. There's really nothing new in the eigenvector stuff. The new stuff is the eigenvalue stuff. So we will see a couple more examples of finding eigenvectors on Tuesday, but really this is all you need to know in order to find the eigenvectors. So we'll see a couple more examples on Tuesday before spending the rest of the time talking about a couple applications of nice things of what we can use eigenvalues for. I guess we'll see that on Tuesday. All right, if you have any questions, let me know. If not, have a good day.